So we wrapped up our last class meeting by working on this example problem. This is an example of a parallel RLC circuit, and we were going through the steps of analyzing such a circuit. Our first step was to calculate the circuit parameters alpha and omega naught, our Neper frequency and resonant frequency respectively, and compare these two values to determine if the circuit was overdamped, critically damped, or underdamped. So we looked at a dead network during the transient condition. So during the transient, our switch was closed, and our dead network means that we have to turn off our independent sources. And we found that alpha was 10 Nepers per second, omega naught was 7.071 radians per second. And since alpha is greater than omega naught, our circuit is overdamped. We then analyze the circuit at t is equal to 0 minus and determine the values for our capacitor current, capacitor voltage, and inductor current at this time. Next, we analyze the circuit at t is equal to 0 plus, using the constraint that the voltage drop across the capacitor cannot change abruptly and the current through the inductor cannot change abruptly, and solve for our inductor current, capacitor voltage, and capacitor current again. And we finished up with step 4, where we analyze the circuit at t is equal to infinity. At t is equal to infinity, the circuit was at DC steady state, so we replaced our inductor with its DC steady state equivalent, a short circuit. We replaced our capacitor with its DC steady state equivalent, an open circuit, and again determined the values for the inductor and capacitor currents as well as the voltage. So what we are going to do now is step number 5. So in step number 5, we are going to apply our response equation. And solve for our waveforms that we're interested in. So let's go back to the very beginning of this problem and look at what types of things we might be solving for. Okay. So our ultimate goal here is to solve for the quantities VR of t and IR of t during the transient condition. So I would argue that the most useful piece of information for us to determine would be the voltage V of t, based on the analysis that we've done to this point. And then once we know V of t, we could solve for VR of t and IR of t. So let me explain what I mean by that, okay? If we apply Kirchhoff's voltage law around this loop, here, we can see that we would have negative V of t plus VR of t plus 20 volts is equal to 0. And from this, our resistor voltage VR of t is simply V of t minus 20 volts. Once we know VR of t, IR of t is simply VR of t divided by 10 ohms, giving us both of our quantities of interest. But we cannot determine either of these two quantities until we know what that voltage V of t looks like, okay? In order to know what that voltage V of t looks like, we have to either also know what the inductor current is or what the capacitor current is. And that's why we solve for actually all three of those quantities. It gives us the most amount of flexibility once we get to this last step here, okay? So I'm going to be solving for my voltage V of t as my primary waveform of interest here at first, okay? So since our circuit is overdamped and looking at our response table, we're going to be using these equations, okay? Because these are our equations for an overdamped system. So let's start by looking at our voltage equation, okay? So our voltage, and in this case, we're considering it to be the capacitor voltage. So I'm going to say VC of t must be of the form A1 e to the S1 t plus A2 e to the S2 t plus VC at infinity. In order to solve this system and determine what the coefficients A1 and A2 are, we're going to need to know what our eigenvalue or natural frequencies S1 and S2 are. For an overdamped system, recall that S1 is simply negative alpha plus the square root of alpha squared minus omega naught squared. And if we substitute in the values that we calculated on Wednesday, we find that S1 is negative, my stylus will write, 2.929 units of per second, okay? S2 is negative alpha minus the square root of alpha squared minus omega naught squared. Plugging in our values of 10 and 5 squared of 2 for alpha and omega naught respectively, we find that S2 comes out to be negative 17.071 units per second, right? And so what we're going to do now is we are going to effectively look at our capacitor voltage waveform at t is equal to 0 plus, okay? So VC of 0 plus is going to be equal to A1 e to the S1 times 0 plus A2 e to the S2 times 0 plus VC at infinity. Well, e to the 0 is simply 1. So this expression reduces to A1 plus A2 plus VC at infinity. And with a small amount of algebraic rearrangement, we find that A1 plus A2 is going to be equal to VC at 0 plus minus VC at infinity. And what we're going to do now is simply substitute in our numerically solved values for VC at 0 plus and VC at infinity. So let's scroll up here and see what we got. So at 0 plus, our voltage V, which is representative of our capacitor voltage, was 0. And at infinity, our capacitor voltage was also 0. So that means that A1 plus A2 must equal 0. And this is our first equation. All right. Now we need to come up with a relationship that involves the derivative of V. Okay. So recall that our capacitor current, stylus will write here, IC of t is equal to C dV by dt, which will be equal to C times, let's look at our table. So we're using this derivative relationship right here. S1 A1 e to the S1t plus S2 A2 e to the S2t. Evaluate this expression at t is equal to 0 plus. We will have IC 0 plus is equal to C multiplied by S1 A1 plus S2 A2. And so let's see, our C value for this particular circuit was 10 millifarads. We found S1 to be negative 2.929. So I'm going to say that, let's see, I see at 0 plus. Let's scroll up here and look at what that was. So 2 amps. Is equal to 10 times 10 to the minus 3, which is our value for C, times S1, which was negative 2.929, I believe. Let me scroll up here. Yep. And I get negative 0.0293 A1. And now I'm going to multiply C times S2. And I'm going to have minus 0.1707 A2. And this is my second equation. Okay. I can solve the equation that I've designated as 1 and the equation that I've designated as 2 simultaneously and get values for A1 and A2. So I will do just that. Okay. So solving these equations simultaneously. So let's see, I'm using my 2x2 system solver. My coefficient for A1 in my first equation is 1. My coefficient for A2 in my first equation is 1. My constant term is 0. My coefficient for A1 in my second equation is negative 0.0293, which I have stored in my calculator as A. My coefficient for A2 is negative 0.1707, which I have stored in my calculator as B. And my constant term is 2. In solving, I find that A1 is 14.142 volts, and A2, excuse me, is negative 14.142 volts. All right. All right, so from here, we know that our capacitor voltage, V of t, will be A1, so 14.142 e to the negative S1, so e to the S1, so e negative 2.929 t, plus A2, so that's going to look like minus 14.142 volts, e to the S2, negative 17.071 t, plus V at infinity, which we found to be 0. So I'm going to put, excuse me, volts here. And from here, the R of t was simply VC minus 20 volts. So that's going to look like 14.142 e to the negative 2.929 t minus 14.142 e to the minus 17.071 t minus 20, and IR of t is simply VR of t over 10 ohms, which will look like 1.414 e to the minus 2.929 t minus 1.414 e to the minus 17.071 t minus 2 amps. So what we're going to spend the next several minutes doing is actually simulating this circuit's response during the transient condition and seeing whether or not our analytical solution matches the simulation. Okay, so give me just a moment to reset up my computer here. We're going to come over to LT Spice and draw our circuit. So I have a voltage source. This will be V1 here in the middle. I'm going to have another voltage source. This is going to be my 20 volt source that I'm placing down here. And let's just go ahead and start wiring some things up. So this is going to be my 10 ohm resistor. I'm going to have another 10 ohm resistor across the top. While I'm at it, let's go ahead and put this 10 volt source here, 20 volt source here. And I'm just drawing the branches where I'm going to place my capacitor and my inductor. So we have a 2 Henry inductor. Excuse me, I shouldn't have put that H there. And we also have a 10 millifarad capacitor. All right. So because LT Spice uses nodal analysis, we need to establish a ground. I am of the habit of always choosing the negative polarity terminal of my capacitor voltage as ground. And I'll explain why here in just a second. Another thing that I am going to do is I'm going to label my positive polarity terminal of my capacitor voltage as VC. So that will be this node up here, okay? So for LT Spice to do the analysis of what's going on in our transient condition, we need to give it initial conditions, which is effectively telling the LT Spice how the circuit was behaving for t is equal to 0 minus. In particular, we need to give LT Spice a value for the capacitor voltage and a value for the inductor current. So I'm going to come back over here to our work, scroll up, and look at our analysis at t is equal to 0 minus. Here we go. Excuse me, I went slightly too far. Our voltage was 0 volts. So that means our capacitor voltage had a value of 0 volts. And our inductor current was 1 ampere. So coming back over to LT Spice, I'm going to click this button on the top middle that says .op. This is how I enter in Spice directives or Spice commands. So to give myself an initial condition for my capacitor voltage, I'm going to type dot or period IC for initial condition, space, V, open parentheses, VC, close parentheses, equal 0. So this is saying effectively that the voltage at node VC is starting off at a value of 0. And now I'm going to press Control M to give myself a new line. Dot IC I L1, the current through inductor 1, was equal to 1 amp. I'm going to put this Spice directive code here. And now I'm going to play around with my simulation parameters, okay? So typically speaking, I tend to look at alpha as a inverse of a time constant. So in this case, our alpha was 10. So I'm going to look at our circuit starting out for 0.5 of a second, because I think that's a reasonable estimation of how long it's going to take our signal to decay until its final value. It might take longer than this, it might take shorter than this, and we'll edit as we need to, but I usually start with effectively 5 times the reciprocal of alpha is giving me ballpark how long I need to look at this thing. Okay, I'm going to run my simulation command. And it's going to start off with nothing, okay? So the first thing that I'm going to do here is I'm just going to click on my capacitor voltage. This is not the signal that we were explicitly looking for, but we did do some work for it. So I want to see whether I did that right. So I click my voltage probe on the positive polarity terminal, and I get this waveform. I can see right off the bat here that it doesn't settle to 0 in this half of a second. So I'm going to change my transient analysis, and I'm going to look at it for 1.5 seconds just to see how this goes. Oops, looks like I didn't actually change it. My apologies. There we go. And we can see that it's getting pretty close to settling at 0. So let's just make it 2.5 seconds just to really hit home. And now it's good and settled at 0, which is what we expect it to be at infinity, okay? What I'm going to do now is I'm going to right click on my graph and I'm going to press the Add Traces button. And down here for expressions to add, instead of using any of the waveforms that our simulation generated, I'm literally just going to type in our mathematical expression that we developed for VFT. So to remind myself of what that was, let's scroll down here. So 14.142. 14.142 times E, which LT Spice needs as EXP, negative S1, so 2.929 times T, LT Spice's time, minus 14.142 multiplied by the exponential of negative 17.071 times time. I press OK. Says I have a syntax error. Okay, for my first 14.142, it looks like I put a comma instead of a period. So let me fix that real quick. All right, so what just happened is that the blue line completely overlapped the green line, which means that our analytical solution for the capacitor voltage perfectly matches that of the simulation. Now, sometimes we will have the right answer, but LT Spice will try to trick us, okay? So there's a couple of things that I want to point out here, okay? We have a scale on the left-hand side of the circuit that spans from 8.8 down to 0, and we have a span from 8.8 down to 0 on the right-hand side of our circuit as well. If I change this just arbitrarily to 12, our answer is still just as correct, but our waveforms don't overlap each other because the scales on both sides don't match. So that's one thing that you have to be very, very careful to look for. You need to make sure that the scale on the left-hand side of your plot and the scale on the right-hand side of your plot are literally the same things. If they ever aren't, you can change the range by right-clicking on the vertical axis and then setting it the same, right? So the top value should be 8.8, the bottom value should be 0, and as soon as I do that, I see perfectly overlapping, which is what I should expect if I get it right, okay? So now let's talk about how we could actually look at the waveform that we are interested in, okay? So I'm mousing over this node right here. Hopefully you can see this, but in the bottom left-hand corner, it's calling this node 002. So what I'm going to do is I'm going to plot my resistor voltage as, I'm going to right-click here and add a trace. So this should be the voltage at node VC minus the voltage at node 2, which is the voltage drop over my resistor. It's showing up in green. And then I'm just simply going to edit this guy right here to subtract 20 volts from it, because that's what my resistor voltage waveform should look like. And voila, again, I have perfectly overlapped waveforms where the scales are the same on both sides. This is how we are going to use LT Spice to check our work in literally every transient analysis problem that we do in this class. In all of your homework sets, on your exam, all of that kind of good stuff, I believe I ask you to use LT Spice to plot your response equations in order for you to check your work every single time, okay? So any questions about using LT Spice to verify our analytical solution? All right, since nobody is saying anything or typing anything into the chat, I'm going to assume that we are all okay. And what we're going to do now is move along to series RLC circuits. Okay. All right. So let's say that we have the following circuit. Where we have a voltage source Vs connected to a switch. And we have some resistor R, some inductor L, and some capacitor C connected like so, where I'm going to define my current I. So this is representative of the inductor current flowing in this direction. And I'm going to define my capacitor voltage Vc of t such that the current I will flow into the positive polarity terminal during the transient condition. I'm going to define my resistor voltage Vr of t, where the current I is flowing into the positive polarity terminal. And finally, we'll have our inductor voltage VL of t like so. And for the sake of argument right now, let's say that our switch is opening at t is equal to 0. Okay. So at t is equal to 0 minus, our circuit is going to look something like this. Recall that for t is equal to 0 minus, we are at DC steady state. So our inductor is going to look like a short circuit and our capacitor is going to look like an open circuit. Okay, so at t is equal to 0 minus, our switch is still closed. Here is our resistor R. Excuse me, our inductor should be a short circuit. Our capacitor over here should be an open circuit. And here is VR of 0 minus. Here's VC of 0 minus. Here's VL of 0 minus. And here is I of 0 minus. Okay. So by inspection, we can see that VC of 0 minus is equal to VS, and I of 0 minus is equal to 0 amps, which means our capacitor has some fixed amount of stored energy, and our inductor isn't currently storing any energy since there's no current flowing through it. Okay. For t greater than or equal 0 plus, our circuit is going to look like this. And what's going to happen is that our energy stored in our capacitor is going to be distributed to the inductor and resistor, which will in turn cause some inductor current I of t to flow around this loop until the resistor converts all of the stored energy into heat. So if we apply Kirchhoff's voltage law around our loop containing the resistor, inductor, and capacitor in series, what we will find is that VR of t plus VL of t plus VC of t is equal to 0. And we can express all three of these voltages in terms of that common current I of t that's circulating clockwise around this series loop. Okay, so our resistor voltage VR of t using Ohm's law is simply going to be R times I of t. Actually, let me move this down. Our inductor voltage VL of t is given by L di by dt. And finally, our capacitor voltage is given by 1 over C times the integral from T naught to T of I of T prime dt prime plus some initial condition on the capacitor voltage VC at T naught, or 0 in our case. Set this equal to 0. All right, so once again, we have an integro differential equation, and we are going to do the exact same thing that we did for this series RLC integro differential equation as we did for the parallel RLC integro differential equation that we developed. We're simply going to take the derivative of both sides, giving us a second order differential equation, right? So we're going to have R times di by dt plus L times second derivative of I with respect to time plus 1 over C times the 0th derivative is equal to 0. And all I'm going to do now is slightly rearrange this equation by making sure that the coefficient of my second derivative term is 1. So in essence, I'm simply dividing both sides by a factor of L. And in doing so, I will find that I have an expression di by dt squared plus R over L di by dt plus 1 over LC t. And this is my characteristic differential equation for my system, much like we had on Wednesday's class for our series RLC circuit. So I'm going to put a box around this guy. This is a differential equation that governs the behavior of our circuit. And now we have to effectively determine what the function I of t is in order to solve this differential equation. So we are going to guess that I of t will be of the form a e to the st, just like we did on Wednesday's class. And if I substitute this guess into my differential equation, what I get is s squared AE to the ST plus R over L times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And I'm simply going to move my common factor of A to the left-hand side. Inside these brackets, I will have an S squared plus R over L times S plus 1 over LC times E to the ST is equal to 0. And oops, we again have a characteristic polynomial. This characteristic polynomial is a second order polynomial or quadratic. So once again, we will use the quadratic equation. So S1 will come out to be negative R over 2L plus the square root of R over 2L squared plus the square root of 1 over LC squared. Sorry, that line ran over some things. Which we'll call negative alpha plus the square root of alpha squared minus omega naught squared. And S2 will come out to be negative R over 2L minus the square root of R over 2L squared plus the square root of 1 over LC squared, or negative alpha minus the square root of alpha squared minus omega naught. And at this point, we observe that alpha for a series RLC circuit is simply R over 2L. Omega naught for a series RLC circuit is the square root of 1 over LC. And at this point, literally everything is identical. Everything beyond this point is identical to what we covered when we derived our expressions for parallel RLC circuits. When alpha is greater than omega naught, we have an overdamped circuit. When alpha is equal to omega naught, we have a critically damped circuit. And when alpha is less than omega naught, we have an underdamped circuit. So if we look back at our table of parallel series RLC responses, you can see that I've summarized those relationships in here as well, right? So anytime alpha is greater than omega naught, we have an overdamped response. For a parallel RLC circuit, alpha is given by 1 over 2 RC. For a series RLC circuit, alpha is given by R over 2L. For both parallel and series RLC circuits, omega naught is given by 1 over the square root of LC. And then we have our generic expression for our overdamped response, our derivative-based relationship for our overdamped response, and then our mathematical definition for S1 and S2 in terms of alpha and omega naught. And that effectively repeats for our critically damped case and our underdamped case. So this one table here is used for all parallel RLC circuits and series RLC circuits. And I've tried to make it as clear as possible that the only real difference between these two types of circuits is that the alpha value is different. Okay. All right, so what I would like to do now is look at an example problem. Go to the right paper here. All right. So let me see if I can find one very quickly here in this textbook that will allow us to look at a different type of response. I think this one is a winner. Okay, so here is our circuit of interest. We are going to have a 1/4 Henry inductor here. A 1 ohm resistor here. This will be a switch that is going to be opening at t is equal to 0. We have a 5 ohm resistor here. And a 12-volt source here. On this right-hand branch, we are going to have a 4/5 farad capacitor. And a 24-volt source, like so. Let's define some things here. So let's consider this voltage with this particular polarity to be our capacitor voltage. This voltage with this particular polarity to be our inductor voltage. And this current will be our inductor current, I of t. And during the transient condition, this current will also be flowing through the capacitor, so it also serves to be our capacitor voltage. Okay. And our quantities of interest, let's do our inductor current and our inductor voltage, just so that I can walk you through the steps of determining these things, okay? All right, so this is our circuit of interest. The first thing that we are going to do is step 1. We are going to look at this circuit during the transient condition as a dead network and calculate alpha and omega naught, okay? So as a dead network during the transient condition, what we are going to have is our inductor, which is 1/4 of a Henry. We have our resistor, 1 ohm. Our switch is going to look like an open circuit because we're during the transient condition. Here is our 5 ohm resistor, and our 12-volt source has been turned off because we have to be looking at a dead network. Here is our capacitor. It is 4/5 of a farad. And then we have this branch over here to the right, where our 24-volt source has been turned off. So we see a series combination of a 1 ohm resistor in series with a 1/4 Henry inductor in series with a 4/5 farad capacitor. The 5 ohm resistor will not contribute to the transient response of the circuit because it is not part of a closed current carrying loop. Here, alpha is R over 2L. So that's going to be 1 ohm over 2 times 1/4 of a Henry. So we have an alpha of 2 neppers per second. Omega naught is the square root of 1 over LC. Which comes out to be 2.236 radians per second. And since alpha is less than omega naught, our circuit must be underdamped. Are we all okay to this point? All right, nobody's saying they're not okay, so let's just keep on keeping on. Our next step is going to be to analyze the circuit. Oh, let's see what's going on in the chat here. All right. So our next step is going to be to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, our circuit is going to look like this, where I'm replacing my inductor with a short circuit because we're at DC steady state. My switch is closed. Here's my 5 ohm resistor. Here's my 12 volt source. My capacitor is an open circuit. Here's my 24 volt source. And let me label our quantities of interest. So here is VC of 0 minus that we need to determine. Here is VL at 0 minus. And here is IL at 0 minus. So let's start with the lowest hanging fruit here. VL at 0 minus will always be 0 volts because the voltage drop over a short circuit has to be 0. Okay. The next easiest thing to determine, in my opinion, will be, excuse me, I should call this I at 0 minus. I at 0 minus. The reason why I say that is because we know that any current that leaves the 12 volt source will flow through the 5 ohm resistor, then through the 1 ohm resistor, and then back down like this. None of it can branch off and flow through the 24 volt source because of the open circuit that's representing the capacitor. So from this, just using good old Ohm's law, we can say that I of 0 minus is 12 volts over 5 ohms plus 1 ohm, looks like 2 amps. Our last thing will be to determine VC at 0 minus, okay? So I'm going to get VC at 0 minus by doing KVL around, excuse me, let me change this color. this loop, okay? So I'm gonna have negative 24 volts plus DC at 0 minus plus 5 ohms times the current flowing down through the 5 ohm resistor, which is negative 2 amps plus 12 volts is equal to 0. So from this, VC at 0 minus is going to look like 24 volts plus 10 volts minus 12 volts, which comes out to be 22 volts, if my math is correct. So let's see, 24 plus 10 is 34, 34 minus 12 seems like 22 to me. I just want to check my KVL equation to make sure I haven't made any simple mistakes here. Because my current is flowing in this particular direction, I should have a negative 10 volt drop. Yeah, all right. So from here, VC of 0 minus is equal to 22 volts. All right, anybody have any questions, comments, or concerns regarding my analysis here at t is equal to 0 minus? All right, so now we'll analyze our circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is open. Our inductor will look like a current source, and our capacitor will look like a voltage source, right? So our inductor will look like a 2 amp source direction down. The reason for this is because we know that the inductor has to be carrying 2 amps of current down at t is equal to 0 plus, because it was carrying 2 amps of current down at t is equal to 0 minus. Here we have our 1 ohm resistor. We have our 5 ohm resistor and our 12 volt source down here. They don't really do anything, but I'm going to be consistent and continue to draw them. Our capacitor is going to look like a 22 volt source having the same polarity as VC. And then here is our 24 volt source. I'm going to label our quantities of interest. So VC at 0 plus, we know that VC at 0 plus has to equal 22 volts because that's what it was at 0 minus. Here is IL at 0 plus. IL at 0 plus has to be 2 amps because that's what it was at t is equal to 0 minus. And then lastly, we have EL of 0 plus, which we do not know. Okay. So in order to determine VL at 0 plus, I'm going to apply Kirchhoff's voltage law around this loop. So starting at the bottom right-hand corner, I have negative 24 volts plus 22 volts plus 1 ohms times 2 amps plus VL at 0 plus is equal to 0. So VL at 0 plus is equal to 24 volts minus 22 volts minus 2 volts, or 0 volts. Does anybody have any particular problems with our analysis at t is equal to 0 plus? All right, so now we're going to analyze our circuit at t is equal to infinity. At t is equal to infinity, our circuit is at DC steady state conditions and our switch is open. So I'm going to replace my inductor with a short circuit. I'm going to replace my capacitor with an open circuit. Labeling my quantities of interest, I'm going to have VC at infinity. I'm going to have I at infinity and VL at infinity. And I can see that VL at infinity must be 0 volts because it's the voltage drop over a short circuit. I at infinity must be 0 amps. And I say that because my inductor isn't part of any closed current carrying loop anymore because of the open circuit from the capacitor and the open circuit from the switch being opened. There are no voltage sources that are connected to my inductor anymore. And from that, I can also see that VC at infinity has to be 24 volts. Which I would get by doing KVL around the outside loop with the understanding that the current flowing through the 1 ohm resistor is 0 amps. All right, so there's my analysis at t is equal to infinity. We only have 10 minutes left of class, so I'm trying to decide whether or not that's enough time to finish this problem up. Let's go ahead and get started and just see what happens. All right. So our quantities of interest in this case are our inductor current and our inductor voltage. Because our circuit is underdamped, IL of t, which is the same as I of t, will be of the form B1 cosine omega dt plus B2 sine omega dt, excuse me. All of this is multiplied by a factor of e to the minus alpha t. And then we have to add to this IL at infinity. So our first step here will then be to determine what omega d is. So omega d, by definition, is the square root of omega naught squared minus alpha squared. Just to be sure about this, I'm going to go to my table. Here's my definition for omega d. Got it right. So let's throw in our numbers. All right. So 2.236 squared minus 2 squared is equal to 1 radian per second. All right, so at t is equal to 0 plus, we will have IL of 0 plus is equal to B1 cosine omega d times 0 plus B2 sine omega d times 0 e to the negative alpha times 0 plus IL at infinity. So cosine of 0 is 1, sine of 0 is 0, e to the 0 is 1. And what this reduces to then is simply B1 plus IL at infinity. Rearranging slightly, B1 is simply IL at 0 plus minus IL at infinity, where IL at 0 plus was 2 amps. Let me double check that. Yep. IL at infinity was 0. So this is just going to be 2 amps. So we already have one of our 2 coefficients solved for. Okay. Now we need our derivative-based relationship, which will be the inductor voltage. So VL as a function of time is given by L di by dt, which is going to look like L multiplied. Now I'm going to look at my table here. I'm using this relationship. So omega d B2 minus alpha B1 times cosine omega dt. And I believe I have minus omega dB1 plus alpha B2, but let's just double check that. Yep, minus omega dB1 plus alpha B2. All right. Times the sine of omega dt e to the minus alpha t. And going to the next page. VL at 0 plus is going to then look like L times omega d B2 minus alpha B1 cosine omega d times 0 minus omega d B2, excuse me, B1 plus alpha B2 sine omega d times 0 times e to the negative alpha times 0. I'm just going to refer back to the table real quickly here to make sure I got all these coefficients in the right order. Omega d B2 minus alpha B1, omega d B1 plus alpha B2. Okay. And once again, cosine omega d goes to 1. Excuse me, cosine 0 goes to 1. Sine omega d goes to 0. E to the 0 goes to 1. And we are left with VL 0 plus is going to be L times omega d B2 minus alpha B1, right? So I'm just going to do a little bit of algebraic manipulation here, right? VL of 0 plus divided by L is equal to omega d B2 minus alpha B1. Now I'm going to add alpha B1 to both sides so that I have VL 0 plus over L plus alpha B1. And this is going to be equal to omega d times B2. So I'm just going to divide both sides by omega d. And if I plug in my numbers here, so let's see, VL at 0 plus was 0 volts. So that makes this whole first term go to 0. Alpha was 2. B1 was 2, I believe. Let's check there. Yep. And omega d was 1. So that makes B2 4 amps. So from this, I of t is going to be B1. So that's 2 cosine, omega d is 1. So 2 cosine t plus 4 sine t e to the minus 2t amps. We recognize that I at infinity was 0. To calculate VL, our first coefficient for VL is simply going to be this bit, L times the quantity omega d B2 minus alpha B1. So that is going to be 1/4 multiplied by omega d, which is 1, times B2, which is 4, minus alpha, which is 2, times B1, which is 2. So our first coefficient for our voltage term is going to be 0. So VL t is going to be 0 cosine t, so I'm not going to bother writing that bit. Our second coefficient is going to come from this bit right here, multiplied by L. So I'm going to have negative 1/4 times omega d, which was 1, times B1, which is 2, plus alpha, which was 2, times B2, which was 4. So I'm going to have negative, 5/2 sine t e to the minus 2t volts. And there we go. You guys could take the time to simulate these results, or excuse me, simulate this circuit on LT Spice and make sure our analytical results match those of our simulation. It's 9:15, so I'm going to stop talking. What I have planned for Monday's class meeting is literally just working another example problem or two, trying to reinforce this stuff. So very specifically, I'm going to work a problem which has a critically damped response, because we haven't yet had an example of that. And I'm also going to work a problem that includes a dependent source in the system to talk about how we'll handle that. And once we wrap those two example problems up, we will be finished with class on Monday and be moving on to our analysis of general RLC circuits, where a general RLC circuit is a circuit that is not a series RLC circuit or a parallel RLC circuit. So anyway, we're wrapped up for the day. I have gone ahead and already put up all of your homework assignments and your exam for this transient analysis section of the class. So it would be very much in your best interests to start working on some of this stuff this weekend. All right, thank you guys and have a great weekend.